Okay, hello. Quick video covering a couple of small topics that are going to get us ready for this week's videos, which are all about the fundamental theorem of calculus. So, sort of loose ends. What can you do with integration? What is integration? It's kind of like finding the area under a curve, but I would like to now convince you that actually it's a more general process, and we're going to see two examples right now. Suppose you want to find the volume of a cone. I may or may not have mentioned this on the very first day of school, but the area problem, the problem of the ancient Greeks of finding the area inside curved objects, was also, well, part of that same problem was not just finding the area inside curved two-dimensional objects, but also finding the volume inside curved three-dimensional objects. And so the process by which we figure out the volume of a sphere, for example, and the way in which this was done in ancient Greek times and the way in which this is done in middle school, if you teach the formula, is by a sort of baby calculus process of splitting up the region into infinitely small pieces and adding them all back up. So we're just going to do this right now. Here is something which, depending on your geometry background, actually I would like to know what kind of proof you've ever seen of this. We have a cone, a regular circular cone with radius A and height B, and it's a right cone in the sense that the the vertex of the cone is the line connecting the center of the circular base to the vertex of the cone is perpendicular to the plane of the circle, so all kind of like normal stuff. And what is the volume of this cone? Well, you've been told since middle school that it is 1/3 of the volume of the enclosing cylinder. Why is this? It's quite hard to prove this in a basic geometry class. If you had a really good geometry class, or if you watched the videos from the beginning of the semester where I did this, the reason why we said that the volume of a cone is 1/3 is because, well, the volume of any pyramid is just 1/3 of the enclosing cylinder. And why? Well, we sort of proved it for a triangular pyramid by decomposing a cube into a bunch of square pyramids and showed that each of those was 1/3, and then we sort of waved our arms and said, there you go. Okay, well, with the power of calculus, we can now give a strong argument for this. And the idea is, if I want to find the volume of something, well, just like we solved the area problem, given some sort of region that we wanted to find the area of, if that region was curvy, how did we deal with that? Well, we split it up into an infinite number of infinitely thin rectangles. And via this method, we approximated the area, and our approximation became sort of perfectly good as the number of rectangles went to infinity. Similarly, we may calculate the volume of this cone by splitting it up into an infinite number of infinitely small things of which we do know the volume. And so what I would like to do now is to take this cone and kind of, take some pieces. What we're really going to do is we're going to take this cone, let me make this picture a little bit better, and we're going to partition the height. Boom, 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 boom. And what we're going to do is we're going to say, okay, well, the volume of this cone is basically just the volume of this cylinder. Oh boy, having trouble drawing here. This is a cylinder, and then here's kind of another cylinder. And okay, I'll just do that. Imagine this all being sort of 3D. And here's another cylinder, and all of these cylinders, whose radii keep getting smaller and smaller. If you add them all up, then the volumes of all of them, then what you're going to get is the volume of the cone. Okay, and this can be seen. This is a child's toy that I have here. This is like stacking little pieces. So okay, here we have something which is roughly in the shape of a cone. And as you can see, this cone, okay, the top is like weird or whatever, so just ignore that. But we have 1, 2, 3, 4, 5, 6. And what are these things? Well, they're kind of like little cylinders, okay? Ignore the hole for a minute because that's just there so that they stack. But what we see, we have cylinders of sort of different radii. And if we add up the volumes of all these cylinders, then that's going to give us an approximation of the volume of the cone. So let's just get right to it. Here's what we're going to do. I'm going to take, and this is kind of an intro to something we're going to do in the last week. I take a line, and I want this, so I go out here to this point B, and I want my, and I want my radius to be A. And so what I have done is I've made this line. And what is this line? It's just a line with, that goes to the origin with slope, I don't know why I'm having trouble drawing this, with slope A over B. So this is in fact just the line y equals A over bx. And well, what am I going to do with this line? I'm going to take sort of this triangle here, and I'm going to take this triangle and I'm going to rotate this triangle about the x-axis. And I hope everyone sees that since this length is b here, and since this height is a, then when you rotate this triangle about the x-axis, what you're going to get is precisely a cone of a volume, or precisely a cone that we want to find the volume of. Okay, and so how am I going to do this? Well, I'm going to do the same old, split this interval from 0 to b up into subintervals. And so let's do it the normal way, would be to let delta x be, well, the total width of the interval is b, so we're just going to have b over n. So this first point here is, is b over n. The next one is 2b over n. The next one is 3b over n, etc. And we're going to go out to I times b over n. And when we're all done, we're going to get n times b over n, which is of course just b. Okay, and on the ith subinterval, I have a rectangle. And well, actually, I guess I could draw sort of all of them. So that's the rectangle drawn on the ith subinterval. Of course, the first rectangle is drawn on the first interval, and the second one on the second, etc. But now, these rectangles are not the things I'm trying to calculate. What we've done previously is we found the area of all these rectangles and add them all up. Now, what we want to do is to see what happens as these rectangles get rotated about the x-axis. And the answer is, maybe you can see this, maybe not, maybe I'm going to draw this well, and maybe not. Maybe continuing to do it in purple is a good idea. But when this purple rectangle on the ith subinterval gets rotated about the x-axis, what's going to sort of be formed is a cylinder. A cylinder with a certain height and a certain radius. And, okay, let's see, just to sort of finish this picture here, when we rotate this whole thing about, we're going to get this whole... Oh, man. Try a little bit harder here to do a good job. Cha-cha. Okay? And I guess, well, trying my best on this picture. And we get a little bit of that. Okay, and so, what might you ask is the thickness of this cylinder? Well, the thickness of this cylinder is the width of this subinterval, and the radius of this cylinder is just the height of this rectangle. And so if I want to find the volume, let's just do it right now. If I want to find the volume of this cone, then what I want to do is to go to the ith subinterval and take that x value, and that x value is, well, in fact, maybe first we'll just call it x sub I star. Okay, and I want to plug that x value into the function, and what I get when I plug that x value into the function is a certain height. That height is the radius, and so if I take that radius, square it, and multiply by pi, then what I have is a certain radius squared times pi gives me the area of the circle, of that circle. And then I multiply by delta x. That gives me, if I multiply the area of that circle by the thickness of that subinterval, that gives me the volume. In fact, what I'm just calculating is just sort of the volume of one of these guys. Maybe I'll use the big one. Oh yeah. The volume of one of these cylinders is just going to be the area of the circle times the thickness of the cylinder. The thickness of the cylinder is just delta x, and the height or the radius of the cylinder is just the height of the function. And if I add all of those up from I equals 1 to n, then I'm going to be adding up the volumes of all of these cylinders. That's going to give me the volume of the cone. Okay, so what is this actually? It's the sum from I equals 1 to n of pi times, well, what I'm actually plugging in is, of course, the value on the ith subinterval. And the value on the ith subinterval is b over n times I. In other words, the ith subinterval, the x value, the x of the sample point is that. And then the width is b over n. Okay, continuing on over here, that's just the delta x. Continuing on over here, what is the actual function? Well, we already agreed that the actual function is the function just y equals a over bx. And so I want to plug b over ni into a over bx. What do I get? I get a over b times the input, which is b over ni, and it is that thing which is being squared times b over n. Okay, and now what's this? This is the sum from I equals 1 to n of pi times, well, the b's cancel, and I just get a squared over n squared I squared times b over n. Okay, and let's see if I've done that right. I think I have. A squared b over, oh no, a squared over n squared. Yeah. Okay. Maybe it's actually easiest to just kind of think of it like this. It's like a over n I quantity squared times b over n. Okay, so continuing, what is this? It's the sum from I equals 1 to n of pi times a squared b over n cubed I squared. But this can be simplified quite a lot because everything is a constant except for the I. So what we get is the sum from I equals 1 to n, what we get is all these constants come out. So I get pi a squared b over n cubed times the sum from I equals 1 to n of I squared. And now I just reach for the formula. And the formula says that this is, so I have pi a squared b over n cubed times, what's the sum from I equals 1 to n of I squared? It's n plus 1, 2n plus 1 over 6. Okay, and so this whole thing becomes, let's see, I can cancel one of the n's, and I'm left with pi a squared b over, well, I'll just say times
2n squared plus 3n plus 1 over 6n squared. And what happens is that as n approaches infinity, all of this goes to 1/3. And that is why we end up with 1/3 pi a squared b as the volume of this cone.
Okay, what is the sort of whole point of doing this now? The whole point of doing this now is even before we learn some fancy new big things that are going to change our whole world, which is going to happen, well, this week, already we've seen that integration, in fact, I didn't even really use the word integral at any point, anywhere on this entire page, but the integral process, the process of splitting up some interval into a bunch of small subintervals and finding some particular small quantity and then sort of adding up an infinite number of them, this is essentially integration, can already solve sort of amazing problems from ancient times and some things that you've sort of seen before. We can now, this is a precise proof, a kind of a calculus algebraic proof of the formula for the volume of a cone. Okay, good. That was one thing. And then two more sort of small loose ends, and then we will call it a day with this video. Sorry, looking for my eraser. Very sad. Yeah. Okay. Guess I'll just use these. Very sad. Okay. So let me just erase this really fast. Okay. Two loose ends. One is an integral property, and one is yet another application of integration that has nothing to do with area. Okay, so first, what should we just call it? One more integral property or something like that. Okay, and this one is also kind of very common sense, I think. And all it says is that if you have two functions, and so here's the theorem. It says if f is greater than or equal to g on some interval ab, then so will the integral from a to b of f be greater than or equal to the integral from a to b of g. Okay, I think the picture for this is quite compelling. You just have some interval ab, and you have some function like this, and that's, say, f. And you have some different function g, and f is greater than or equal to g, so something like this or whatever. And I drew it so that they're, you know, at some moment they're equal, but okay, whatever. If f is bigger than g, this is now the g function, then so should the integral from a to b of f be greater than the integral from a to b of g. Okay, reason, duh, of course that's true. We could almost stop here, but this is sort of so important that we'll do a quick proof of this. And the quick proof just says, okay, we're just going to use the definition of the integral. What is the integral from a to b of f and the integral from a to b of g? It's just what you get when you take the limit of a Riemann sum. And so we will partition this interval up into subintervals, boom, 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 boom. We will choose a sample point from the ith subinterval, x sub I star.
And now I will simply observe that f of x sub I star is certainly greater than or equal to g of x sub I star. Reason, because f is greater than or equal to g everywhere on that entire interval, so of course it's true for x sub I star. Okay, in other words, f is bigger than g here, just duh, boom, boom. Okay, next, I will multiply by delta x. So f of x sub I star times delta x is greater than or equal to g of x sub I star times delta times delta x. Sure. This is just me multiplying both sides by delta x, so of course it's true. How should we interpret this line? We should interpret this line as saying that the area of the rectangle under G is just sort of bigger than the area of the rectangle under F at that sample point. But then, of course, this is true for every x sub I star. In other words, this is true on every subinterval. So since this inequality holds on every subinterval, it's also true that the sum from I equals 1 to n of f of x sub I star delta x is greater than or equal to the sum from I equals 1 to n of g of x sub I star delta x. Okay, so now we're just saying that, okay, if this rectangle is always bigger than this one, and that's true for every single subinterval, then the entire sum will be true. And finally, we just take the limit. If the limit of this, if this is bigger than this, then the limit of this is going to be greater than or equal to the limit of that. And so we get, indeed, that the integral from a to b of f has to be greater than or equal to the integral from a to b of g. Okay, important enough to take a minute and prove it. And this is an integral property that we will use in the sort of very next video. Okay, last thing. Is, and this is, I think, something that are, well, there's a lot of different ways to talk about this, and I'm actually going to talk about it at the beginning of the next video anyway, so I'll give a sort of quick overview of this. What I want to ask about is, what is the average value of some function f on some interval a, b? Okay, and I could just give you, as our book does, the definition of the average value of a function on an interval. But what I would like to sort of draw out a little bit is sort of the common sense notion of what this sort of means and what it kind of should mean. Okay, so you have some function, and you have some starting point of that function and some ending point. And this function is doing, you know, whatever it's doing. And now this function is f. And the question we would like to ask now is, how big is this function on average? Maybe I'll draw the function a little bit differently. How big is this function on average? Okay, well, this is not the kind of thing that you ask so much. This is such a common question, so we have to sort of try to use our common sense a little bit. What does it even mean to say how big is this function on average? Well, what are some maybe common sense ways in which we might want to talk about such a thing? I think one of the best examples would be temperature. So if this is the temperature, and this is maybe A is like the morning, you know, or sunrise or something like that, and B is sunset, then, so this x-axis is time, then you might ask the question, hey, what was the temperature like today? In other words, what you want is a single number which represents what was the average temperature sort of the day. Okay, how hot was it today on average? All right, and first let's just quickly discuss what are probably like a whole bunch of just sort of wrong answers. What's one thing you definitely don't want to do? Well, one thing you don't want to do is to take the sort of temperature at the beginning of the day and the temperature at the end of the day and just average them. I hope everyone agrees that that's just wrong because, well, here the temperature started kind of low, went really high, and then ended kind of low. But if you took the average of these two y values, the temperature at sunrise and the temperature at sunset, then you would say that the day was on average, you know, something like this hot. But that would misrepresent the fact that the temperature actually went quite high in the middle of the day and sort of stayed that way. And so there are sort of these extreme cases that kind of reveal that this can't be the right way to do it. For example, if this is A and this is B, then just taking the average of the beginning and ending temperature wouldn't account for whether the temperature looked more like that. Here you would say that the average temperature was just the starting and ending value, and here, what if instead the temperature went like this? So these two should have totally different average temperatures, so we're sort of losing something from just looking at the first point and the last point. Okay, a slightly more sophisticated answer might be, let's just take the average of the low temperature and the high temperature. So let's just take the highest value of the function and the lowest value of the function. Well, under some circumstances that might not be so bad, but we can also look at extreme cases and see how that's just totally wrong. Because this here, suppose a situation where this was the temperature at sunrise, this is the temperature at sunset. Suppose this day, you know, started off really, you know, chill, and then it got really hot for like an hour, and then sort of cooled down again. Whereas a different kind of day, and maybe it got really hot at the very beginning of the day and stayed hot the entire day, and then sort of ended. Okay, well, these 2 days would have the same low temperature and the same high temperature, but the average temperature of the day would be quite different. So somehow we need to look deeper. It's not the average value of a function on an interval is not just the average of the beginning and the ending point, nor is it the average of the high point and the low point. It's sort of like an entire snapshot of what was going on with that function at every single possible moment. Okay, now it seems the time to sort of ask how you would do this. How would you find the average temperature of a day? Well,
seconds.
Yeah, one thing to do is to just imagine that you are doing some kind of 7th grade science project or something like that, 5th grade science project even, and you want to figure out the average temperature of the day. Well, what you would do is you just take temperature readings. How often? I don't know, once an hour. And in fact, if you look at a day, if you look at some kind of weather app or something like that, and you look at the temperature either recorded or predicted of what the temperature is going to be at every single hour of the entire day, that gives a really good impression of what that day is going to be like. And if you wanted to do a 7th grade advanced science experiment, then you would just take the temperature more often, like every 10 minutes over the entire day. Okay, in other words, let's just go back to the very definition of what an average is. How do you average a bunch of things? You just add them up and divide by the number of things. If I have 5 things and I want to know their average, I just add them all up and I divide by 5. What's giving us pause here is that we don't have a discrete number of outputs. We have sort of an infinite number of inputs and an infinite number of outputs if we have this sort of temperature function. Okay, so all right, here's what we're going to do, and maybe this is now sort of obvious. What we're going to do is we're going to take this interval from A to B, and we're going to partition it up into subintervals. We're going to call this okay. So this is you know x1, this is x2, x3, x4, etc. And then all the way up to b, which is x of n. And then what we're going to do is we're going to choose on each subinterval. This is a more casual science project. You don't quite take the temperature every 10 minutes exactly on the minute. You just take some temperature reading in any given 10-minute interval. In other words, we choose a sample point. We choose a sample point on the ith subinterval, and then we just see what that is. So boop, and what we get is a whole bunch of discrete y values telling us what the temperature is at any given moment. In other words, we just take f of x1 star, a sample point on the first subinterval, and we add it to f of x2 star, a sample point on the second subinterval, plus f of x3 star, a sample point on the third subinterval, and we keep on going all the way until we get to a sample point on the nth subinterval, and then we add all those numbers up, and then we divide by, this is a very unfortunate way of writing this. Yeah, so I'll just kind of write smaller. F of x1 star plus f of x2 star plus f of x3 star plus all the way to f of x of n star. In other words, you add up these n temperature readings, and then you just divide by the number of readings. This, to me, is a direct reflection of the notion of average. Average is you add up n things and you divide by n. Okay, and so what we get here is, if we want to convert this into sigma notation, the sum from I equals 1 to n of f of x sub I star times 1 over n. And now, if you want to make this perfect, what can you do? If you want to make this perfect, you should take the limit as n goes to infinity. Okay, so I hereby propose a definition of the average value of f on the interval AB should be, according to this logic, simply the limit as n goes to infinity of what you get when you take the interval from A to B, divide it up into subintervals, take a sample point from the ith subinterval, plug it into the function, and add them all up, and then divide by n. Okay. This looks a lot like an integral. Is it an integral? It is almost an integral, but for subtle reasons, it's not quite an integral. And that's because an integral is the limit of a Riemann sum, and this is not a Riemann sum. Although it looks superficially like a Riemann sum, if it were truly a Riemann sum, and our partition goes from A to B, then our delta x should be b minus a over n. But here our delta x is not b minus a over n. It's 1 over n. And so to fix this, I multiply by b minus a over b minus a. This is sort of an algebra trick or something, you might say, just so that, and this becomes 1 over b minus a times the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star, but now I have b minus a over n here. And now this is in fact an integral, and what we end up with is 1 over b minus a times the integral from a to b of f. And this is in fact the average value of a function on an interval. And this problem, well, I'll stop talking because I want this to be one video, so goodbye.